Today we're going to have some fun playing with pictures. Not much today, I think. I think you shouldn't have any trouble because most everybody has seen graphs and graphical things, and so most of which you already know, most of the things I'm going to say. But there may be one or two little fine points that you have to be aware of, things that traps you might fall into, and I want to point them out. Okay, so let's get going. Be a little simple to start with. A graph has a bottom axis and a side axis, and usually there's labels on them telling you what the bottom axis and the side axes represent. And there's often numbers on the axes. There don't have to be numbers on the bottom axes. Generally, there's numbers on the side axes. When there are numbers on the axes, the high numbers are for the bottom axes, the high numbers are on the left, the low numbers are on the left, the high numbers are on the right. If they're numbers, sometimes there are no numbers, sometimes it's us and them, or A, B, and C, or January, February, March, April. If there's something like January, February, March, April, generally the progression the time will go from left to right. Okay, so numbers, things that have a progression, will go from left to right. When you're on the side axes, the numbers go from the bottom to the top. So on the bottom are the low numbers, and they get higher as you go up. This is a picture of what's called a scatter diagram. And it represents data that have two variables, say x and y, and maybe this is weight, and this is height. What happens is you take someone and you measure their weight, and you measure their height, and you get a number like 150 and 70 inches. You would find 150 on the bottom scale, 150, and you'd find 70 inches on the side scale, and you would cross them and you'd put an asterisk where those two things crossed. And each of these asterisks on the picture represents a person's weight and height. This person might weigh 175 and be 72 inches high. This person might weigh 160 and be 76 inches high, and so on. And each asterisk or point or X or A or letter or symbol, whatever, on the screen, on the chart, will represent a measurement. Each one is one measurement, but each measurement is made up of two numbers, an X number and a Y number. And you just have to find where the X number is, find where the Y number is, and cross them. And where they cross, that's where you put the dot on the screen. That is a scatter diagram, the usual way of representing data on a diagram. There's two numbers, an X number and a Y number. Frequently you will find that there are lines drawn between the asterisks or X's or symbols on the scatter diagram. Those lines mean nothing at all. They're there just for clarity, to show you where the points are. It's left over from the good old days when the paper was kind of dirty and you couldn't tell the difference between a mark that someone made and just some fly speck. So you put lines between them and let everyone know what and if this is a time axis, for instance, you'll be able to see clearly the sequence in which things are happening. So it sort of magnifies or illustrates or clarifies where the points are. But the lines themselves, for instance, what's going on here, doesn't mean anything. There's nothing going on in between those points. It's only at the points that there's data. There's no data in between the points. So the points really do not signify data. When I say mean nothing, I mean they don't really represent data of any kind. They're just there for clarity. Sometimes on a scatter diagram, you'll see a curve. In this case, it's a straight curve. That generally means that there is a relationship, that although I've observed this weight and this height, or this weight and this height, or this weight and this height, I believe there's a relationship between weight and height. And the true relationship is the points on the line. That is, someone weighing this much should be this tall. Someone weighing this much should be this tall. The points on that line is the points on the relationship. Well, and how come when I made measurements I didn't get points on that line? Well, that's because of measurement error, random error, fluctuations. A person does not everybody's normal. In fact, nobody's normal. So you really can't expect John to be on the line. If he were on the line, he'd be normal. Jane, you can't expect her to be on the line. She's not normal either. Here's Bill. He's a little above normal, okay? The people are, by above normal, I mean above the line, not necessarily above normal. But nobody is on the line, although that's the underlying relationship between the variables. So when you see a line drawn on a scatter diagram, that does mean something. It means that's the proposed relationship between the x variable and the y variable. And generally we call that a regression plot. And it doesn't really have to be a straight line. In this case, you can see it's a curved line. There's a curved relationship between x and y. Here's the x and the y, or whatever variables you put on the two sides. And we think for this x value, the y value should be this big. And for this x value, the y value should be this. But look, I observed somebody, and the y value was that big. Well, that's too bad. He was below what he should be. Or she was below what she should be. It just wasn't on the line like it's supposed to be. The relationship is the line. We assume that this is the correct relationship, and the fact that the others don't hit the relationship is merely what we call experimental error. That's experimental error. We'll be referring to experimental error when we do experiments later on. But that's why things don't hit the line. But the line is a relationship, and that's a perfectly legitimate thing to do. It's not the same as drawing lines between the points. That doesn't mean that's not a relationship. Let's worry about scale now. When you draw these numbers on the thing, if you draw from 0 on up, that's a standard scale. But look what happens sometimes. You put on a standard scale, 0, 1, 2, 3, 4, 5, but the picture is, the line on the thing is between 2 and 3. The lowest value is 2, the highest value is 3, and someone looking at this has an awful lot of wasted space. Look, nothing down here is of any meaning to him, nothing up here is of any use. It's just what's going on in here that he's interested in. So he sort of squints to see what's going on. There's not a whole lot of information, because you've got all wasted space. So sometimes what's done is the scale is made into a detail scale. And instead of going from 0 on up, for example, in this situation, you would make the scale from 2 to 3. This is called detail. A detailed graph would go from something other than 0 on up. So if you have a detailed graph, it starts at some number other than 0, and it goes up. Well, here we see a picture between 2 and 3, and we see it's still a straight line. However, look at the slope. It's not the same as it was before. When we saw the picture before, it sort of looked like that, a little flat. Now it's looking like that. And you have to be careful. They don't look like the same. This line don't look the same. But if you realize that this is a detailed graph and the other one was not, they are the same. And it's very deceiving sometimes. If you don't check the scale carefully, you can be confused as to what's going on. Let me have a better example of that. Here's a company that is rock steady, making $4,000 a month for the last 5 months, and they plotted the last 5 months, and they drew a line through the plots, and it's a straight line, and the company is rock steady, $4,000 a month income. Well, that's great. Nothing wrong with that company. It's a pretty good company. Steady. Someone comes along and says, oh, no, I want to magnify that graph. And this is the magnification. And you can see, you show someone this, hey, look what's going on. That company's, look at that graph. It's terrible. It's terrible. That company's going, let me get my money out of that company. Sell my stock, quick, sell. Well, that's ridiculous. The amount that it went down is $1. $1 in 4,000. You'd hardly sell your stock because the company was making $1 less now than it was 4 or 5 months ago. It's just it's a rock steady at $4,000 or between $4,000 and $4,001. Don't let the detailed graph confuse you, because it will magnify things, and it may magnify things a lot more than you're interested in seeing them magnified. So when you see a detailed graph, beware, beware. It's not wrong to have a detailed graph. It shows more stuff in it, but be careful not to read too much into the detail. Okay? Now, next thing I want to talk about are pictures. Graphs sometimes are represented by pictures instead of regular graphs. Now, in this case, you probably would have A and B or us and them kind of thing, and you want to show the strength of the two armies, say, and you draw a little man, and this one is twice as tall as this one. Well, most of us think in terms of a linear scale here, and this one is this tall, this one is twice as tall, and so this represents twice as many soldiers as this represents. This represents twice as many as this represents because this is twice as big as that. Okay? However, not all graphs, and usually that's the case, and the natural tendency of people is to look at these graphs and see that this is twice as big and therefore it's twice as much. But that's not necessarily the case. Graphs can be represented in heights, as we saw, or in areas or volumes. In heights, this barrel is twice as big as that barrel. So you could say this represents something which is twice as big as that. That probably would be our natural tendency to think of this, let's call this A and B. We probably would say B is twice as big as A, if we just glanced at this picture. However, it's quite possible that they measured the barrel in area rather than heights. Now, in area, if you were to put paint on this, you would find that the paint to cover this would only cover this much of the big barrel. You'd have to have another amount here, another amount there, another amount there. In other words, you'd need 4 times as much paint to cover this barrel as to cover this one, if you were just painting the picture. So if you were talking areas, you might, instead of having 1 and 2, you might have 1 and 4. And you have to look at the scale to see whether they're talking about heights, 1 and 2, this is twice as big as that, or they're talking about 1 and 4, where the scale is amplified, and this is 4 times as big as that. Now that's just area. If you were to actually fill this with liquid, and then pour this in here, you'd only fill up about this much. You'd have to fill up 8 times to get this thing to fill up. There are 8 of these in here, 8 of them. So if you were to talk about volumes, volume scale, you would say 1 for this and 8 instead of 4. For that, you'd have to fill us up 8 times with this in order to fill it up. And so sometimes they talk about volumes, and scale would tell what they're talking about. They won't tell you I'm talking about volume, but they will have to write a scale down here, and the numbers will tell you what's going on. Don't ever look at graphs without looking at the numbers, because you will be confused. You will naturally pick heights, and maybe heights is correct, but it might be area, it might be volume. In fact, if you have something, we've got to be careful now. If you take area, if you have heights, and you take a height which is twice as big, so I got A is 1 and B is 2, then this B has 2 times as much as A. If the heights are 1 and 2, and I'm talking about areas, then I have to sort of take the area, which is height times width, and if they're both twice as big, then 2 times 2 be 4 times as big. And if I'm talking about volumes, and one is twice as big, then this is 2 times 2 times 2, which is width times height times depth, and that would be 8 times as big. So if I had something that looked on a graph which was twice as big, the answer could be 2 times as much, or 4 times as much, or 8 times as much. The only way to tell is to look here. Now it gets to even be more confusing when we have numbers like 3, or 4, or 5, and the trick is to take the dimension. If you want the dimension, just take it if you're comparing heights. If you're comparing areas, take the dimension times the dimension. That'll give you the area relationship. If you want volumes, then take the dimension, the dimension, the dimension, and that will give you the volume. So if they're 3 times as big, if this one is 3 times as tall as that, and I want the volume, I'd have to go 3 times 3 times 3, or 27. 27 times as big. And if I wanted area, it would be 3 times 3, or 9 times as big. And if I had 5, if this were 5 times as tall as that, and I wanted volumes, it would be 5 times 5 times 5, or 125 times as big. So a barrel, 5 times as big, tall, 5 times as tall as this. The dimensions all expanded by 5 times as big in each direction, not just taller, but 5 times in each direction. The volume would be 125 times as big for the bigger volume than the smaller volume. Okay? Now, wasn't very hard stuff. I think you'll have no trouble now looking at graphs. Make sure you look at the numbers and seeing what happens. Okay? Have a good one.